In this video, I'd like to revisit an example that we worked through in class on our last day, and I felt like I rushed through the ending in class. I'd like to take us to that point where we were near the end and then take my time finishing the graph. So I'm not going to start from scratch because I think we did work through the initial steps pretty carefully. I am going to follow the graphing rational functions sheet that you should all have, and if you don't, it is posted in Canvas, so it gives our step-by-step procedure for graphing a rational function. So in this example, f of x equals x squared minus 9 over x squared plus x minus 2. I think we started out by, we found that there are vertical asymptotes at x equals negative 2 and x equals 1. We found those by setting the denominator equal to 0. So I'm going to go ahead and draw the vertical asymptotes. It helps to have a pretty big graph grid for these, and of course it helps to use a ruler to draw these asymptote lines nice and straight. So that's at 1 and negative 2. I have two vertical asymptotes. We also found out in class that there's a horizontal asymptote along y equals 1, that horizontal line. You can, if the degree of the numerator equals the degree of the denominator, here they're both of degree 2, I just take the lead coefficient of the numerator over the lead coefficient of the denominator. In this case, that's 1 over 1 is understood. Y equals 1 is that horizontal asymptote. So I'm going to draw that on my graph. Okay, and so I drew that through 1 on the y-axis, so I have that horizontal line drawn. And we also, I think our third step on our sheet is to plot the x and y intercepts. So we found that the y-intercept was 0, 4.5. And we found that there were two x-intercepts, 3, 0, and negative 3, 0. You find the y-intercept by computing f of 0, plugging 0 in for x. You can find the x-intercepts by setting the function equal to 0, which will amount to setting the numerator equal to 0 and solving for x. So let's plot those points. 0, 1, 2, 3, 4.5. It's about there. 3, 0. So here's 3. And negative 3, 0. Negative 3. So I just have those 3 points plotted so far. We also found out that there's a point where the graph crosses the horizontal asymptote. And we cross the horizontal asymptote at the point negative 7, 1. The way we found this point was we set the function fraction equal to the horizontal asymptote value. So we set it equal to 1 in this case, and we solve for x, and we got x equals negative 7. So negative 3, 4, 5, 6, here's negative 7, 1. We know that point lies on the graph. Now, we know that's the only point where the graph crosses the horizontal asymptote. Graphs may cross the horizontal asymptote, sometimes at one point, sometimes at more. Roy's going to find those out, because once we label those, we know the graph can't cross the horizontal asymptote at any other points. By the way, with the vertical asymptotes, the function's graph can never cross a vertical asymptote under any circumstances. And so now I'd like to go ahead and fill in the graph. All we have are a few points to work from so far. And what I'd like to do is first think about what the horizontal asymptote tells us about the graph. And really, the horizontal asymptote only tells us what the graph might look like when x is very, very large, say to the right, or when x is very, very negative to the left. We know in both those cases the graph has to approach the horizontal asymptote, get very close to it as x gets very large or very negative. So like if I start from my point 3 here, I know as I move to the right, I have to approach that horizontal asymptote. I also know I can't cross it anymore, because there's only one point back here on the negative side where the graph crosses the horizontal asymptote. So I pretty much know the graph has to do something like that as we move further and further to the right. I would say as x approaches infinity, f of x approaches 1. That's how symbolically we could represent this idea of the graph getting closer and closer to that horizontal line y equals 1. So we pretty much know that without plotting any more points. If I think about the negative direction, I guess I might say, well, I can see how the graph might connect from -3 to -7. The graph has to cross the horizontal asymptote there. And yet once it crosses, we know as it moves further to the left, it's got to approach that asymptote. So it pretty much, it's like it has a bump, and then it comes back down and approaches the horizontal asymptote. It can't cross the asymptote again. So it crosses it at -7, 1, rises a little bit above, and then it's just got to come back down close to it again, because as x approaches -infinity, f of x approaches +1 also. Okay? And so I could fill in some points or plot some points and to see this, but we really can reason this out just from what we know about the horizontal asymptote and where the graph can cross it and where it can't cross the horizontal asymptote. The horizontal asymptote doesn't tell us much about what's going on in between, in the middle of the graph. It tells us something about what's going on at the two extremes, far to the right, far to the left. Now we got to figure out the middle portion of this graph, and this is where, if you want, you can plot some more points. In fact, I'm going to set up another table here of x and y values. You can plot as many points as you'd like, but the goal is to kind of try to sketch without having to plot a lot more points. When x is equal to 2, if you plug into the function, so I did this calculation ahead of time, when x is equal to 2, y is equal to -1.25. So I just plugged x equals 2 into the function. So 2, negative 1.25 is about right there. So it seems like as I move to the left of this point, x-intercept at 3, it seems like the graph is coming down. And the graph along that vertical asymptote now has to, as we approach it from the right, we either have to go plunging downward or we'd have to go shooting upward along that right-hand side. We can't cross it. We're kind of deflected either downward or upward. Now, there's really only one possibility here, because sometimes you can use the process of elimination to figure this out. If I wanted to go upward from this point at 2, I would have to cross the x-axis. I'd have to cross the horizontal asymptote. There'd be more points on the graph on the horizontal asymptote and on the x-axis, but there can't be any more. We found the x-intercepts. We found the only point where the graph crosses the horizontal asymptote. So you can't reason that the graph just has to go down toward that vertical asymptote as we move left from the point at 2. But if that isn't convincing to you, what we can also do is, and this is really helpful for me sometimes, is to look just to the right and to the left of x equals 1. So I'm going to look at a couple more values now. So I know when x is 1, and I'm going to write that as a decimal 1.0, I know the y value is undefined. If we plugged in, the function is not defined there. I mean, that's why we have a vertical asymptote, okay, because the denominator would be equal to 0. If I look just a little bit smaller than 1, say 0.9, and a little bit larger than 1, say 1.1, I could plug each of those values into the function to get a sense of where the graph would be just to the right of this vertical asymptote and just to the left of it. And I went ahead and did that ahead of time. You can do this on, of course you would do this on a calculator. It's just a big mess by hand. Do it on a calculator. You could do it in Desmos. I'm not going to work through the steps here, but I just plugged in f of 0.9 and figured out what I get. I had to round off a little bit. It's about 28.24. And f of 1.1 came out to be negative 25.13. Well, these are way off my grid, right? At 1.1, which is just a little bit to the right of the vertical asymptote, I'm getting a very negative y value way the heck down there. Okay, I'm convinced. I know this graph just goes plunging downward. And what we can say in symbols here is I can say as x approaches 1, the vertical asymptote value, with a little plus sign from the right, f of x approaches minus infinity. That's symbols for representing this behavior of the graph. Just to the left of 1 is 0.9. I know to the left of the vertical asymptote, I should be plotting a huge, well, relatively huge, a large y value off my graph. So from this y-intercept at 0.4.5, I know the graph has to go shooting upward in order to hit that 0.9 point with the very large y-coordinate. This shape right here, I would say as x approaches 1 from the left, minus sign means slightly smaller than 1, like that 0.9, f of x is approaching infinity. It will get very large. If I looked at 0.99, I'd have a much larger y value. So I was able to figure out the behavior of the graph on each side of the vertical asymptote at x equals 1. You can kind of reason it out, but if you want, you can also just plug in values of x slightly smaller, slightly larger than the vertical asymptote value, if that helps you. And notice that helped me choose which one of these 4 possible shapes the graph has around that vertical asymptote. Looks like we have the this possibility right there at the x equals 1. All right, now I also could plot a point at -1. And it's not absolutely necessary, but it's not too hard to plug into -1 into this graph. When I plug in -1, that I can do by hand. I get 4, -1, 4. Okay, so the graph is kind of coming down like that, -1, 4. Now, there are 2 possibilities as I move to the left from here. I could go shooting upward along the vertical asymptote, or I could go plunging downward. Process of elimination. If I go plunging downward, I'll have to cross the horizontal asymptote and the x-axis again. We already found the points where we cross those. We can't cross again. There's no way the graph can come down here. The graph has to turn around and go back up along that vertical asymptote. And so that's sufficient. You really don't have to analyze this anymore. But if you again wanted to, if you were uncertain, you could take that x value, which is -2.0, where the function is undefined, and look just a little bit smaller than that, a little bit larger. Now, in the negative direction, slightly smaller than -2 is 0.0 is actually -2.1. That's to the left, and -1.9 we would say is slightly larger, right? That's just a little bit to the right. And you could evaluate the function at these 2 values using a calculator or Desmos. And at -1.9, I got 18.59. Again, it was an ugly decimal. I rounded off at 2 places. At -2.1, I got -14.81. So let's see now. Between -1 and -2 is the -1.9 value, just to the right of -2. So at -1.9, I have a large y value. That sort of confirms my suspicion that this graph had to go shooting up like so along the right-hand side of that vertical asymptote. Here we would say as x approaches -2 from the right, from slightly larger values, the function, the y values, approach infinity. Okay? And at -2.1, which is slightly to the left-hand side of -2, I'm getting a very negative value down here somewhere. So that kind of confirms my suspicion that the graph is going down here as x approaches -2. We would say, with a little minus sign from the left, less than -2, the function approaches -infinity. So there we got the whole graph that I finished very quickly in class. And in another video, we'll do another full graph of a different rational function.